store 3D positions of every single vertex, we can also store the corresponding 2D texture coordinates. And this then leads us to a very flexible way of mapping textures onto 3D objects. So let's say if we have a complex 3D object like this house, and we want to apply textures to this object. Then to do this, we first have to flatten the object onto a 2D plane. And for complex shape, it might not always be possible to flatten the shape as flatten a 3D mesh into one continuous 2D shape. So in order to flatten more complex 3D objects, we often have to split up the object into different parts and then flatten those individual parts of the objects onto a 2D texture. So we can cut the mesh up into little pieces, flatten each one of those pieces, and then we can pack them into what's referred to as a UV atlas, which is just taking all the different flattened pieces of the mesh and then packing them into one 2D texture. And we can then use the coordinates of every vertex on this flattened 2D texture to look up colors from the 2D texture that we should assign to each one of the vertices. Now, in order to perform this unwrapping of a mesh, this is often done manually by artists with the help of 3D modeling tools. And ideally, a good UV map will be one where we can flatten all of the triangles of mesh onto a 2D plane while minimizing the distortion of the triangles. So when we flatten the triangles onto this 2D plane, we want to roughly make sure that the triangle shapes are not changed too much. But unfortunately, constructing an optimal UV atlas for 3D mesh is unfortunately an intractable problem. So trying to find the optimal way of splitting up a mesh into different pieces and flattening that mesh onto a UV atlas, trying to find the optimal partitioning of the mesh can be very difficult. So in practice, this is done either manually by hand by an artist, or we can use some heuristics to try to automatically construct this UV atlas. But again, these heuristics might give you a reasonable UV atlas of a mesh, but might not necessarily give you the optimal packing. Okay. So any questions about this UV mapping technique? Okay, so for the most part, it's just flattening a 3D mesh and then storing the texture coordinates for every single vertex. Now, once we've constructed this UV map, the texture coordinates are stored at the vertices of our mesh. But when we are rendering the surface of a mesh, we have to determine the color that we should assign a point inside each triangle. So if we only have the texture coordinates at the vertices of a mesh, we somehow have to determine the texture coordinates that we should assign to points inside a triangle as well. And to do this, we can again use barocentric interpolation. We can take the texture coordinates that's stored at the vertices of a triangle, and we can apply barocentric interpolation to interpolate those texture vertices to any point inside a triangle. And we can use those interpolated texture coordinates in order to sample from our 2D texture. So the interpolation procedure is exactly the same as what we apply for interpolating colors, but now we're interpolating texture coordinates as well. Okay, so that's more or less the main idea with texture mapping. And now we're going to look into some of the implementation details that are important for correctly implementing texture mapping in practice. So one of those details is that when we are interpolating texture coordinates, we have to be careful about where we perform this interpolation. So when sampling from the texture, this is often done during the interpolation and sampling stage of a rasterization pipeline. And this stage happens after we've projected all the triangles onto our image plane, and we now want to determine what color we should assign each of the pixels that are covered by the triangle. So at this stage of the rasterization pipeline, we've already projected all of the vertices onto the 2D plane. So we've taken a 3D triangle and we've projected it onto a 2D image. And one of the problems that we'll encounter when applying texture in sampling at this particular stage of the pipeline is that if we perform interpolation in the 2D image coordinates, we might not get the correct result as if we perform the original interpolation in 3D coordinates. So for example, let's say I have this line in 3D space, and I've projected this line onto a 2D image. Now, when we perform the projection of this line, we take points along this line. So for example, let's say we take V0 and V1, the endpoints of the line, and we project them onto a 2D image. But now if you look at the midpoint of the line, which lies between the two endpoints, and we project that onto the image plane, what we are going to see is that the distances between the midpoint and the two endpoints end up becoming distorted. So even though the midpoint is in the 3D coordinate system is equal distance to both V0 and V1, after they have been projected onto the image plane, the midpoint is no longer equal distance between the two endpoints. And this and kind of the cause of this effect is that distances in 3D are not preserved under perspective projection. So when we project 3D points onto a 2D plane, the distances between various points, the proportions may not be preserved. So points that are equally distant apart in 3D space may not be equally distant once we've projected them onto the 2D image. And this can lead to some problems with texture mapping. When we are performing barycentric interpolation, if you recall, to calculate the barycentric interpolation weights, we look at the size of like the different triangles that's constructed by splitting a big triangle into 3 smaller triangles. But since distances are not preserved under perspective projection, if we calculate the barycentric coordinates in screen space after projection, we can get different barycentric interpolations than if we calculated the barycentric coordinates directly in 3D space. And the issue that this can lead to is that it can cause distortions in the textures that we map to our 3D shapes. For example, let's say I have this 3D checkerboard pattern, and I want to map this onto just a simple rectangle. If we perform barycentric interpolation in screen space after perspective projection, and we used up those barycentric coordinates to interpolate the texture coordinates, then we can end up getting incorrect texture coordinates that lead to distortions in the original checkerboard pattern. So this is not the result that we would get if we perform interpolation in the original 3D coordinates. So this then leads to a little bit of a kind of a tricky implementation detail. Because because texture sampling is applied after 2D projection, at that point, we no longer have access to the 3D coordinates of the original vertices. So we only have the 2D projected vertices, and we somehow have to figure out the correct interpolation for the 2D coordinates in order to sample from our texture. And this becomes a general problem when we are applying barycentric interpolation for anything in 2D space. So if we want to interpolate, let's say, vertex colors or vertex normals after we have performed perspective projection, then applying in barycentric interpolation in the 2D space will end up giving us incorrect interpolated results. So one way that we can fix this issue is that we can just store the 3D positions of all of the vertices. So we keep track of both the 2D coordinates of the vertices after projection, as well as the original 3D coordinates. And then whenever we have to perform interpolation, we just perform those calculations using the original 3D coordinates. So this will work, but introduces some additional overhead of having to keep track of both the 3D coordinates and the 2D coordinates of the vertices. But now it turns out this is kind of a clever little trick that we can use to calculate the correct barycentric interpolation in 2D coordinates without requiring access to the original 3D coordinates. And that is by using a perspective correct interpolation. The way that this interpolation technique is going to work is that it's going to perform interpolation using slightly different values than, right. Okay, so let's go through the details. With perspective correct interpolation, instead of interpolating the original values at the vertices, so let's say instead of interpolating the original texture coordinates that are stored at the vertices of our mesh, we're going to instead interpolate kind of a depth projected version of those texture coordinates. If u and v correspond to the original texture coordinates of the vertices, instead of directly interpreting u and v, we are going to divide u and v by depth. So z corresponds to the distance of the point from the camera. So we are going to divide the texture coordinates by the depth first, and then we are going to interpolate those depth projected values instead. Okay, so to see how this works, let's run through an example. So let's say I have this triangle. We have the 3D coordinates x, y, z, and then we have the 2D texture coordinates u, v stored at the vertices of the triangle. Z here corresponds to the distance of the vertices from the camera. So the x, y, z coordinates have already been transformed into the camera's coordinate frame. Given a point P in the middle of the triangle, we want to interpolate the texture coordinates that's defined. We want to interpolate the texture coordinates from the vertices to that particular point P. So to start, let's calculate the interpolated u coordinate. So let's say we've calculated the barycentric interpolation weights W0, W1, and W2. These barycentric coordinates were calculated using the positions of the vertices after they have been projected onto the image plane. So we're not going to have access to original x, y, z coordinates anymore. Okay, so let's say we've used the barycentric, we've calculated these weights. And then the next step is that we are going to calculate the depth projected values for the particular quantity that we want to interpolate. So if we want to interpolate the u coordinate for the texture coordinates, we just take the u coordinate defined at all of the vertices, and we are going to divide it by the depth z. We're then also going to calculate one additional value at the vertices, which are the inverted depth values. So here we just take the z coordinate of every vertex, and we just take the reciprocal of that. So for each of the vertices, we are going to calculate 1 divided by the depth of that vertex. Now, to calculate the interpolated values, we are going to apply just regular barycentric interpolation on the depth projected values. So u prime here corresponds to taking all of the depth projected u values and then interpolating them using the barycentric coordinates that we calculated in screen space. Okay. And then we're going to apply a similar barycentric interpolation to the inverted depth values as well. So big Z here corresponds to the interpolation of the inverted depth values at each of the vertices. And now to recover the original u coordinate, as if we have performed the barycentric interpolation in the original 3D coordinates, we just take the interpolated u prime value and then divide that by the interpolated inverted depth value, big Z. And this would then give us the interpolated u coordinate, as if we have performed the interpolation in the original 3D space. And we can apply this method to calculate any interpolated value we want in screen space. And it would then give us the correct values as if we had performed those calculations in the original 3D coordinates. Yep, question.
I don't know if I agree with wrong, I thought you said the interpolation rates, we don't have access to the original XY coordinates. Then how do you know what then zero, Z1, Z2 to calculate the?
Oh, right. Yeah. So this is going to assume that when we are projecting the triangle onto your image plane, when we perform that projection, we also do this projection for all the attributes of the triangle. So like let's say when we are projecting this onto the image plane, when we perform that perspective projection, we also divide all the attributes like normals, texture coordinates by the depth as well. Yeah, question.
To confirm, we similarly complicated and about each data.
Yeah, that's right. Yeah, so you calculate all these values for each of the vertices, so then you can interpolate them for the fragment shape. Okay, any other questions about this? Okay, so for a lot of these rasterization pipelines, we can apply this perspective correct projection to interpolate all of the attributes at the vertices. So this will fix one problem with texture mapping. But in practice, there's also another another implementation detail that we have to be careful of when applying texture mapping. And that is aliasing. So for every pixel that we draw on our image, we might have to sample from a texture in order to figure out the correct color that we should assign that particular pixel. But this sampling process from our texture can lead to some aliasing artifacts, depending on how far away an object is from the camera. So for example, one type of aliasing artifact that we can observe are magnification artifacts. This corresponds to the bottom case in this figure here, where the camera is looking very close to the surface of an object. So in this case, every pixel in the image will be mapped to a relatively small area on our texture. So this is saying that the size of every pixel is much smaller than the size of a texel in our texture. And this can, right? Okay, yep. So and we'll show an example of what these magnification artifacts look like. The second type of aliasing artifact are minification artifacts. This corresponds to the top case here, where the camera is very far away from the object. So in this case, the size of a pixel in our image can be mapped to a large area in the texture. So one pixel can cover multiple texels in our texture. And if these aliasing artifacts are not handled correctly, they can lead to some visually jarring issues when applying textures to an object. So here we have a checkerboard pattern that's applied to a plane. At the bottom of the image, this corresponds to points that are close to the camera. So this corresponds to the magnification case, where every pixel is mapped to a very artifacts on the texture pattern, rather than nice smooth edges as we would normally expect. But as we move towards the top of the image, this corresponds to points that are getting further and further away from the camera. And at the top of the image, we see some examples of minification artifacts, where a pixel in the image maps to a large area of the texture. So when a pixel covers many texels in the texture, depending on how we perform that sampling procedure, we can end up seeing these artifacts where the original checkerboard pattern that we started with starts getting distorted and corrupted. And at some point, it starts looking like random noise. So if we want to correctly apply textures to an object, we have to be able to handle these different types of aliasing artifacts in order to mitigate any visually jarring artifacts. Okay, so to see how we can fix these different types of artifacts, let's take a look at some of the different cases. Let's take a look at each of these cases one at a time, starting with magnification artifacts. Magnification artifacts happen when we are looking very close to the surface of an object. So this is when a pixel is mapped to only covers a very small area in the original texture. So for example, let's say if I have this very simple 2x2 texture, and my pixel end up mapping to this particular point in the texture. So a simple sampling procedure could be that when I just sample the pixel that's closest to the point that my pixel maps to. So if my pixel is mapped to some point in the texture UV, I'm just going to sample the color of the closest pixel. So in this case, it would be the top right pixel. Okay, right. Okay, so this is fine. But let's say as we move this coordinate around in texture, then the color can change abruptly if we suddenly snap from one pixel to another. So this can lead to discontinuities in the color that we assign points on the 3D surface, where depending on which pixel is closest to the point of to the texture coordinate of a particular pixel, we can get sudden changes in the color that we assign to adjacent points in our image. And this then leads to some of the stair-step artifacts that we saw in the previous checkerboard pattern. Now, one way that we can mitigate these magnification artifacts is by using bilinear interpolation, where instead of snapping to the closest pixel, we're instead going to try to interpolate between the colors of the 4 nearest pixels to a particular pixel. So for a particular pixel, let's say it maps to a given point on our texture UV. We can find the 4 closest pixels to that particular point. And now instead of just sampling the color of the closest pixel, we're going to smoothly blend between the colors of all 4 pixels that surround this particular point. So to do this, we're going to define a new coordinate system centered around this 2x2 region of pixels that's closest to our point. So here, we're going to define a new set of coordinates, S and T, where 0, 0 is going to be on the bottom left pixel. And then as we move towards the top, the pixel on the top right, it's going to be assigned a coordinate of 1, 1. So given a point UV, we can map it into this new coordinate ST. And we can then use these S and T coordinates to interpolate the colors of these 4 neighboring pixels. So first, we're going to interpolate horizontally by using the S coordinate. So we're going to blend the color of the bottom 2 pixels, and then we're going to blend the colors of the top 2 pixels using S as the interpolation values. Now, once you have interpolated the color of the bottom row and the top row, you then perform one more interpolation using the T coordinate to interpolate between the colors of the top row and the colors of the bottom row. And we can then use this final interpolated value as the color for our pixel. So if we interpolate colors all along this 2x2 region of pixels, we get something that looks like this, where depending on where we are within this 2x2 neighborhood, we can get a smooth blending of the colors of the 4 neighboring pixels, instead of having a sharp transition whenever we snap between one pixel to another. And by performing this smooth bilinear interpolation, we can then smooth out some of the jagged artifacts that we saw before. So on the bottom left, we were using the nearest pixel as the color for a particular pixel. and we get some jagged edges on the checkerboard pattern. But by applying this smoother bilinear interpolation, we can get smoother edges for our checkerboard pattern on the bottom of this image. Okay, so bilinear interpolation is one method of mitigating some of these magnification artifacts. Any questions about this? Nope.
It's like the two-dimensional region has a lot of contrast and colors, but again, in this case, checkerboard is black, white, black.
Yep.
Would it end up squeezing a lot of the gray?
Right, yeah, so the interpolated values will look more gray, but as you get closer to a particular texel, it's like interpolating colors on a triangle. As you get closer and closer to a particular texel, the interpolated value will just converge to the color of that particular texel. Yeah.
That one kind of looks gray. Or is that unrelated?
What? Right, yeah, so if you look at some of the pixels that are bottom edges here, you will see some gray colors. But then I think that's something that's needed in order to render these smooth edges instead of kind of the jagged stair-step patterns that we saw without bilinear interpolation. Yeah, any other questions about this? Okay, then let's take a look at how we mitigate the other type of artifact, which are minification artifacts. Minification artifacts happen when we are looking very far away from an object. So in this case, one pixel in our image maps to a large area in the texture. So this means that the color of a particular pixel, a pixel covers multiple texels. So the color of a particular pixel depends on multiple texels rather than just a single texel. So in this image here, at the top of this image, so for this particular image, we are just using the color of the closest texel that a pixel maps to. And because a pixel can cover multiple texels, adjacent pixels can end up being mapped to very different parts of the texture. And if we just use a single texel for the color of a particular pixel, we can get some of these random changes in the colors between adjacent pixels. And that can end up leading to these large distortions in the pattern of the original texture. Yep. So to correctly determine the color of a pixel in this minification case, we need to take into account the color of all the texels that are covered by a particular pixel. So when we map a pixel onto a texture, we need to somehow sample the colors of all the texels that are covered by a particular pixel in order to get the correct averaged color that we should assign a given pixel. So one way to do this is that whenever we sample from a texture, whenever we detect that a pixel covers multiple texels, we should just sample all the colors from all the texels that are covered by that particular pixel, and then average those colors together in order to determine the final color we should assign a particular pixel. So this brute force approach can be fairly expensive because now for every pixel that we want to draw, we might have to sample multiple texels in order to determine the correct color for that pixel. If an object is very far away, one particular pixel can potentially cover hundreds of texels. So this process can be extremely expensive. So one way that we can make this a bit more efficient is by pre-computing these averages before we apply the texture for rendering. So one particular data structure that we can use to pre-compute these textures is what's called a MIPMAP. So the idea for MIPMAP is that we can take our original texture and then we can compute smaller and smaller versions of the texture by averaging multiple pixels in the original texture into smaller textures. So here, let's say we take our original texture, we can construct a texture that's a quarter of the size by averaging 4x4 texels together into a single texel. So for every texel in the smaller image, this corresponds to an average of a 2x2 region of texels in the original image. And as we construct smaller and smaller versions of this texture, every texel will correspond to an average of a larger and larger region in the original texture. If we get down to a texture with just a single pixel, this corresponds to a texture where the texel just becomes the average color of the entire texture. And with these mipmaps, we can then construct an image pyramid that corresponds to smaller and smaller versions of our original texture. So now with these mipmaps, we can sample from these smaller versions of the texel in order to get an average color from a large region of the original texture. So for example, let's say if we determine that a pixel covers a 2x2 region of the original texture, instead of sampling 4 different texels from the original texture, we can just sample a single texel in the first level of our mipmap pyramid. And this would and just by looking up a single texel on this smaller version of the texture, you can get the average value of a 2x2 region in the original texture. And if we need the average color of a larger region, we just have to sample from a higher and higher level in this mipmap pyramid. And this then allows us to get the average color of multiple texels just by using one single texture lookup. Okay. Now, in order to apply these mipmaps, one of the things that we have to determine is that what level of the mipmap pyramid should we sample from? So the idea is that if the pixel covers a large region of the original texture, then we should sample from a higher level, this mipmap pyramid. So we need some way of estimating how large, we need some way of figuring out what's the size of a pixel when it's projected onto our texture. So to do this, we can use some heuristics. So here we have a simple equation to determine the level of the mipmap that we should sample from. So in order to determine this level, we're going to take advantage of the fact that when we are rasterizing a triangle, we are often trying to we're coloring in multiple pixels at a time. So when we project a triangle onto a 2D image, we find all of the pixels that are covered by that triangle, and each one of those pixels have to sample from the texture in order to find the correct color for that particular pixel. So if we want to know roughly what the size of a pixel is when projected onto the texture, we can look at how quickly the texture coordinates are changing between adjacent pixels. So dx and dy here corresponds to the change in texture coordinate between the pixel on the left and the pixel that's sorry, how quickly the texture coordinates are changing between horizontal pixels and vertical pixels. So that we are coloring in, we can look at its left neighbor, we can look at its texture coordinates, and we can use that to figure out dx, which corresponds to how quickly the texture coordinates is when we are moving horizontally. And then dy can be computed by looking at, let's say I have my current pixel, and we can look at the pixel that's immediately below the current pixel. We can calculate the difference between those two texture coordinates and then use that as the dy value. And we can then, so once we have figured out how quickly the texture coordinates are changing between adjacent pixels, we can just plug those values into this equation to determine which level of the mipmap we should sample from. So if the texture coordinates are changing faster between adjacent pixels, then we are going to get a higher level of value for L, which means that we should sample from a smaller version of the texture. Okay, right. Any questions about this? Okay, so one question that you might have is that in order to construct this map pyramid, how much more additional memory do we need to store the map compared to the original texture? Yep, question. Oh, we won't be asking you to take logs or square roots, so it's fine. If we ask you to perform calculations, it'll be very simple that you can just do by hand.
Oh, so what's it called?
Yep, it won't be. So for the final exam, you shouldn't need calculators or any devices. Yep, question.
Just to confirm here, for the EXT line, the syntax, like if that's a horizontal or vertical distance. We just want to clarify what's the squaring with the square root of it, or would it cancel out, or it's
Oh, right. Yeah. I think the square is mainly so that because the changes in texture coordinates, I guess, could be negative. So the square, you can probably replace that with an absolute values. Okay, right. Okay, yeah. So one question we might have is that how much more additional memory do we need to store the maps compared to the original textures? To figure this out, we can try to visualize the map pyramid. So we can take this original texture and we can split it up into its individual RGB channels. So now if we want to construct the next level of the map pyramid, we are going to get a texture that looks like this. So here we have a texture that's a quarter the size of the original image, and we've split up its RGB channels into just separate textures for this visualization. And if we compute the next level, we'll get a texture that looks like this, and we can repeat this process. And so hopefully it should be relatively clear that from this visualization, the amount of memory that we need to store the entire map pyramid is just about a third of the extra. We just need a third of the extra memory that we need to store the original texture. So storing the whole map pyramid actually doesn't require that much more additional memory compared to storing the original texture. So these maps can be a very efficient way of fixing some of these aliasing artifacts for texture mapping. Okay, right? Okay, yeah. So this is everything that I want to cover for texture mapping, and this is going to be so as part of your assignment 4, we will be asking you to implement some of these texture mapping techniques. So you can refer to this when implementing that part of the assignment. Let's see. Yep, probably 9 enough time to start the next lecture. So I guess any questions about texture mapping before we wrap up for today? Okay, then for Friday's lecture, we're going to try to finish up. We're going to try to cover everything for shader programming. Might be a little bit tight on time, but after Friday's lecture, you should have everything that you need to complete assignment 4. So any final questions before we wrap up for today? Okay, if nothing else, then I'll see you on Friday.